Have you ever stopped to think about how your voice, which is just a vibration in the air, can travel across the world in a blink? Well, it's not magic. It's this incredible hidden engine of our modern world called digital signal processing, or DSP. It's pretty much the secret language that powers everything. Your phone calls, your music streaming, you name it. And in this explainer, we are going to decode that language.
This is really the central question, isn't it? If you can answer this, you can start to understand how our entire connected world actually works. We're talking everything from the phone in your hand to the satellites circling the globe.
All right, here's our game plan. We're going to start with the basic problem. How do you turn sound into data? Then we'll look at the first real solution, see how engineers made it way smarter and more efficient, and finally, we'll touch on how our gadgets actually recognize these signals in the first place.
Okay, let's dive right in. At its core, the challenge is this. Sound is an analog signal. Think of it like a smooth, continuous, flowing wave. But computers, they only speak digital, a very different, kind of choppy language of ones and zeros. So, the big question is, how in the world do you translate between the two without losing all the important stuff?
You know, the first idea engineers came up with was this sort of brute force approach. They just said, hey, let's just take thousands and thousands of little snapshots of the sound wave every single second and write down the value for each one. This really foundational technique is called pulse code modulation, or PCM.
So, let's get into the nuts and bolts of PCM. How does this fundamental method of turning a smooth wave into a bunch of numbers actually work? Well, it's basically a three-step dance. First, you've got sampling, where you take all those snapshots, thousands per second. Second, you quantize it. This is where you round off the value of each snapshot to the nearest level on a scale you've already defined. And finally, you encode that level into a binary number, a string of ones and zeros. It's kind of like creating a digital flipbook of the sound.
But yeah, there's a catch. That whole rounding off step, the quantizing, it's not perfect. There's always this tiny little difference between the real analog value and the digital level it gets snapped to. This difference creates an error. It's like a faint digital hiss or static. We call this quantization noise, and really, minimizing it is the name of the game.
Now, this is where things get really clever. Engineers realize something important about human hearing. We're way more sensitive to mistakes in quiet sounds than we are in loud ones. So instead of using the same size measurement steps for everything, they developed something called logarithmic compression. This technique uses super tiny, precise steps for the quiet parts of a signal, and much bigger, broader steps for the loud parts. It focuses all the accuracy right where our ears are going to notice it the most.
And here's the payoff, right here. By being so smart about where to focus the precision, this method gives you the quality of a 12-bit signal while only using 8 bits of data. That is a massive efficiency win. You're getting much higher quality for way less data.
So PCM is a great start for sure, but it's a bit of a data hog because it treats every single one of those thousands of samples as a brand new piece of information. But what if it isn't? What if there's a more efficient way to think about this? And that's where differential PCM, or DPCM, comes into play. It's built on a really powerful observation. A sound wave doesn't just jump around randomly, right? Each sample is almost always very, very close to the one right before it. So, instead of encoding the full value every single time, DPCM predicts what the next value will be and then just encodes the tiny difference. Think about it this way. PCM is like describing a car's exact GPS coordinate every second. DPCM just says it moved 5 feet forward. Way more efficient.
And, I mean, the results really do speak for themselves. Just look at the data rates here for high-quality speech. Logarithmic PCM needs about 64 kilobits per second, but DPCM, by just smartly encoding the differences, gets you pretty much the same quality while chopping that data rate completely in half, down to just 32 kbps. That's a huge leap forward.
But why stop there? We can get even smarter. Human speech isn't uniform. The volume and power change all the time. So the next step is adaptive DPCM. This version has a quantizer that actually adapts on the fly. It uses smaller, more precise steps when you're whispering and larger steps when you're shouting, squeezing every last bit of efficiency out of the signal.
Okay, now we're going to take a really radical leap in thinking. This is linear predictive coding, or LPC. Instead of trying to meticulously encode the waveform itself, LPC asks a totally different question. What if we just model the source of the sound? And in this case, that's the human vocal tract.
So LPC creates this digital model of a human throat and mouth. And then
Instead of sending the sound, it just sends a tiny packet of instructions. For voiced sounds, like your vowels, it's like telling the model to vibrate at a certain pitch. For unvoiced sounds, like shh, it's like telling it to just push out a burst of noise. So you're not sending a recording of the sound, you're sending the recipe to recreate that sound perfectly from scratch on the other end. Wild, right?
So far, we've really been focused on how to code a signal to send it efficiently. But DSP is just as important on the other side of things, receiving and actually detecting those signals. And a perfect example is something pretty much all of us have done, pressing a key on a telephone keypad.
This is the magic behind what we call touch tones. The official name is dual tone multi-frequency, or DTMF. Every time you press a number, your phone generates a unique sound that's actually a combination of two pure sine waves, one low frequency that comes from its row and one high frequency from its column. So when you press the 5 key, you're creating a sound that is a perfect mix of 770 Hz and 1336 Hz.
So how does the telephone network know instantly that you pressed 5? I mean, it could run a full complex frequency analysis on the sound, but that's slow and a total waste of processing power. Instead, it uses this super specialized DSP tool called the Goertzel algorithm. You can think of it like a highly trained sniffer dog that's only looking for a few very specific scents. It's a hyper-efficient technique designed to do just one thing and do it fast. Listen for those exact touch tone frequencies and completely ignore everything else.
Okay, so we've looked at coding schemes from the simple to the incredibly complex, and we've seen how detection algorithms can be super lean and mean. So when you put all this together, what's the big picture? What's the main takeaway?
Well, when you take a step back, you realize the DSP is really this constant, elegant balancing act. Every single technique we've talked about is a trade-off. Do you want absolutely perfect quality? Okay, but you're going to pay for it with a high bit rate, like with PCM. Or do you want an incredibly low data rate that requires way more computational brainpower to decode, like with LPC? It's this continuous negotiation between quality, data size, and the processing power you need to make it all happen.
From that simple idea of just sampling a wave to the complex modeling of the human voice, these DSP techniques are the engines running silently inside our entire digital world. They are what make it all possible. And, it leaves us with one final thought. As we demand more data, faster speeds, and richer experiences, what clever new balancing act are engineers going to have to invent next?